Hello everyone, this is a group assignment for DDB 41103 Surface Engineering for the Group 4. So there are 5 team members. First is Noshami, second is Adif, third one is me and Junjin, fourth is Adip and Yogendran. So for the case study, our title is question 2. The Anson Corporation is experiencing issues with the gas and wind turbine blades. The several incidents involving the process of harm linked with the blade failures. Analyze the issue and suggest a surface engineering technique that can be applied to extend the blade's life.
A very good day to everyone. My name is Yogendran, son of Subramani, metric number CD210005. Today, I'll be presenting a case study on turbine blades failure at Anson Corporation. Our focus will be on identifying the causes of these failures and how surface engineering can help prevent them. Firstly, turbine blades, whether in gas or wind turbines, operate under extreme harsh conditions. Gas turbine blades are made of nickel-based alloy and must survive temperature beyond their melting points. Even with cooling system, they suffer from oxidation, corrosion, and erosion due to ash, sand, and other particles. Other than hand, with turbine blades, which are very large composite structure, face long-term fatigue and weather damage from rain, hail, and dust. These problems can severely reduce blade strength and lead to failure. At Anson Corporation, these challenges are not just theoretical, they are real. They experience multiple failures, including visible cracks, leading edge gouges, and complete blade breakage. These issues not only threaten safety, but also lead to expensive shutdowns and repairs. The failures are caused by a combination of mechanical erosion, fatigue, chemical breakdowns, and heat stress. Here's the role of surface engineering to overcome the problem. It involves applying specified coating and treatment to the blade surface. These coatings act like a protective shield that slow down damage from erosion, corrosion, and heat. By strengthening the outer surface, we can significantly extend the life and reliability of the turbine blades. Next is degradation and failure mechanism. These are the 4 main types of blade degradation that we must understand. First is mechanical erosion, which comes from particles like sand or rain hitting the surface. Secondly is the fatigue, caused by millions of repeated stress cycles. And then the third one is the chemical erosion, degradation by oxidation and corrosion. And finally, thermal stress from temperature changes can cause coating or the blade material itself to crack. Let's take a closer look at erosion damage, which is one of the most critical issues in gas turbines. High-speed ash and dust wear away the blade surface. Steam condensation can also contribute to erosion. In wind turbine, the leading edge of blade is constantly hit by rain, hail, and debris, especially at the blade tips, which is more at high speed. This erodes the protective surface and exposes the inner structure, leading to cracks and moisture damage. These images shows that erosion damage actually looks like. On the left, you see gas turbine blades affected by particle erosion. In the middle, wind turbine blades show clear sign of leading edge wear. And on the right, we see surface pitting at the material lost due to weather impact. These visual signs are early warning of deeper structural issues. Thank you.
My name is Muhammad Alif Nazmi bin Nordin. My matrix number is CD210297. Next is a fatigue failure from cyclic loading. Blades endures billions of loading cycles, blade-wise, edge-wise bending, causing microscopic damage. Transverse crack, perpendicular to fiber, fiber breaks, and debonding. Cracks weaken load transfer, enable moisture ingress, and often start at stress concentration. Example like trailing edge or root. Wang show adhesive joint in trailing edge are fatigue prone with thicker adhesive accelerative crack growth. Gas turbine blades face cyclic thermal, centrifugal, and vibrative stress, leading to early fatigue. Transverse crack in composite accelerate elimination. In metals, they reduce load capacity. Critical insight: stress riser defect adhesive joint, initiate crack that grow with each cycle. Unrepaired cracks linked up, causing sudden failure below design strength. Next is environmental degradation, oxidization, and hot corrosion. Environmental degradation in turbine blades, high temperature challenge, 800 to 1100 Celsius. Oxidization and hot corrosion from fuel ash, salt, sulfur chlorine, vanadium. Protective alumina scales on nickel alloys and coating, aluminate, resist degradation. Thermal barrier coatings insulate but can be compromised. Failure mechanism, molten salt dissolve outside layer, causing heating and material loss. Heats become crack initiation site, accelerating fatigue. Without protection, oxidization salt, opposite lead to rapid blade degradation. After that is thermal stress and cycling effect. Thermal stress and blade degradation. Gas turbine blades face extreme thermal cycling during starts and shutdown. Cause thermal shock to stress metal and coatings. Common failures: spallation of ceramic top coat due to oxidization of bond coat, thermal expansion mismatch to micro cracks coating flaking. Wind turbine blades face milder but long-term thermal effect, such as UV exposure and temperature swing in rising. Photo oxidization and heat near glass transition. Point damage fiber matrix bond. Over time, surface micro cracks form and weaken structural integrity.
I will explain on surface engineering solutions. So the gas and wind turbine blades face the relentless attack like the erosion, corrosion, fatigue, and thermal stress, which will lead to the degradation and reduce the service life. The solution of surface engineering is applies the specialized coating and treatments, shut the critical components from degradation pathway. So our goal is extend the blade service life significantly. So for the benefits, it will preserve the blade integrity in extreme environment, enables a higher operating temperature, reduce maintenance costs, and also extend the replacement intervals. For advanced surface modification technology, our range is from the thick deposit to atomic scale thin films. So the target-specific failure modes include of thermal spray coatings to prevent the combat particulate erosion, diffusion aluminizing to resist the oxidation or corrosion, shock panning to suppress the fatigue cracks, and also the multi-layer thermal barriers to mitigate the thermal stress. So for the surface engineering solution, First is a HVOF, high velocity oxygen fuel and plasma spray. So they deposits the ultra hard coatings that act as a sacrificial shock. So in gas turbines, the HVOF lays down the turbines like WC, COCR on the leading edge. For steam or wind blades, the CMAX fight water or dust erosion. So the plasma spray also applies the MCR ALY alloys for thermal or oxidation resistant. So the advantage of HVOS is extreme hardness, dense, wear-resistant surface, drastic erosion rate reduction, and for the critical consideration, include of the adhesion integrity must be ensured, thermal expansion mismatch with substrate, and the plasma spray preferred for the thermal barrier coatings TBCS. So the second surface engineering solution is laser cladding. So the core function is to rebuild or overlay the black surface with wheel-resistant alloys and form a metallurgical bond through the laser melt, substrate, and the powder. The key application is in place repair of the eroded blades, especially the leading edge, and restore the thickness without blade removal. Also, it will provide the erosion-resistant sharps, for example, the stellite overlays. So in literature review, the brand ETAL 2009 state that the high-quality erosion-resistant protection sharp on the leading edge. Advantages of the laser cladding, including of the precision control, robotic system, dense bonding, and the proven results is 100 of the steam turbine blades repaired or on site in reference 11 and significant life extension for the damaged blades. So the third surface engineering solution is duplex surface treatment, the aluminizing and the shock pinning. So step one is diffusion of the aluminizing, forms the Al2 or 3 skew through the NiAl intermetallic layer. The benefit is the high temperature oxidation or corrosion resistant. Second step is a shoot panning, bombards the surface to induce a deep compressive stress, and the benefit suppress the fatigue crack initiation and growth. So the synergistic defense mechanism, the aluminizing will prevent the oxidation or corrosion, and mechanism is using the protective Al2 or 3 skill. Shoot pinning will prevent the fatigue failure, and its mechanism is compressive stress barrier. For aluminizing and the shoot panning, the duplex treatment, proven performance is more than 2 times fatigue life extension, industry standard for gas turbine blades, and often paired with the ceramic top coats. So the critical application is on the gas turbine blades, which combine the treatment for extreme temperature or cyclic stress environment, and it will maximize the resistance to oxidation and also the mechanical fatigue. Then the 3.4 is a PET cementation diffusion coatings, which include of the aluminizing and siliconizing. So the core process is chemical infusion of the aluminum or silicon into the black surface to form a protective intermetallic layers. The aluminizing will include of the NiAl, NiAlCl, and I2Al3 phases, while the siliconizing include the silicides for the steel beds. So the key protective function of aluminizing is resist the high temperature oxidation, and the primary threat is the hot corrosion. The siliconizing is resist the oxidation or corrosion, and the primary threat is the steam environments. So the advantages involved of the low-cost uniform coverage on complex geometry like the turbine blades and infra heat treatments to enable the precise control. The operational consideration should be control the diffusion times, critical for the target thickness achievement and also the embrittlement prevention. The fifth surface engineering methods include of the ion implantation, surface hardening. So the core process is bombard the surface with high energy ions like the N plus or Cl plus. It will modify top 1 to 5 micron layer and forms a hardened compounds or microstructure. No thick hot and will result in the minimal distortion. The benefits is the surface hardness using the mechanism hard phase formulation. Also, it will be resistant and fatigue strength. So the targeted application is like for the small turbine components, surface limited damage prevention and erosion prone thin edge, not for the large blades because the penetration depth is a limitation. Critical constraint is the shallow penetration depth microns and the cost effectively only for specific components, optimal for the pre-existing compressive stress needs.
Next, I will present about electrochemical deposition, electroplating. What is electroplating? Electroplating deposits metal like nickel or chromium to enhance corrosion resistance. Next is often used on cooler gas turbine, part lines casing and shaft, not hot blades. In wind turbine, thin metal coating can protect from lightning strikes. For example, electrodes nickel plating improve erosion and corrosion resistance on turbine blades. The next one is shock pinning, mechanical pinning, a co-working process where small shocks impact the surface, inducing compressive residual stress. And this delays fatigue crack initiation and significantly extend fatigue life, and commonly used after coatings to improve blade durability, especially at high blade loads. Thermal barrier coatings or plasma spray. What is a thermal barrier coating? A materialized system of metallic bond coat. The plasma spray YZ insulates blade, reducing metal temperature by up to 200 degrees Celsius. Extend life by preventing thermal fatigue, oxidation, and overheating. Thin film coating CVD or PVD. Ultra-thin hard coating deposit via chemical or physical vapor deposition. The material is resist corrosion and erosion in hot environment. Also includes nano coatings for wind blade, for example soldiers, with carbon nanotubes to protect from rain erosion without adding weight.
Hi, my name is Noshami Liang, metric number CD210342. I will present about discussion. So let me start by summarizing the core problem Anson Corporation is facing. Their gas and wind turbine blades are failing due to four major factors, which is a physical erosion, fatigue from repeated stress, environmental corrosion, and thermal stress. For example, gas turbine blades are cracking and suffering from heat-induced coating failures, especially in high temperature zones. Meanwhile, wind turbine blades are getting eroded along their leading edge and developing cracks from constant wind loading. These failures are not just a technical problem, they are causing real operational downtime and safety risks, which is why surface engineering is so important. To tackle this issue in surface engineering, for gas turbine, we use thermal barrier coating. This acts like insulation, lowering the temperature of blade metals by up to 200 degrees Celsius and reducing thermal fatigue. Then there's HVOF, high velocity oxygen field coating, hard layers that take the heat from dust or ash erosion instead of the blade itself. Pack aluminizing adds a corrosion resistant surface that great for high heat zones. On the wind turbine side, we apply HVAF, which is a high velocity airfield cement coating, to shield the blade edge from rain and debris. Should pinning introduce beneficial compressive stress into the material, which help stop cracks from growing. Lastly, laser cladding is an amazing repair technique, which is it let us restore worn blades right on site, saving both time and money. So what happens when we bring all these techniques together? We interrupt the failure pathway, meaning the blades last much longer, need fewer repairs, and operate much more safely. For gas turbine, the combination of thermal coating and erosion-resistant layers tackle heats and particles. For wind turbine, combining erosion coating with short pinning builds resistance against both weighting and fatigue. And looking ahead, advanced nano coating like those with carbon nanotube are showing promise, especially for extra protecting against moisture and UV. Overall, surface engineering isn't just a fix, it's a smart investment that brings down costs, improves safety, and boosts long-term performance.